As we continue to look at the variety of organic compounds, we now turn our attention to IR spectroscopy because this is a very useful technique to get information on functional groups, or more specifically, information on bond types. In this video, we're going to begin with a brief introduction to spectroscopy. In general, spectroscopy is based on the interaction of matter with energy in a non-destructive manner. And one of the important considerations is the idea of the wave-particle duality of electromagnetic radiation. With spectroscopy, we need to think about electromagnetic radiation both as particles and as waves, kind of at the same time. So a photon is a particle of light, or a particle of energy. And each photon has a particular amount of energy. Then we can think of a quantum as a packet of energy. And so each packet has a particular amount of energy. Now, different types of radiation have photons with different sized packets of energy. So for example, X-ray photons would have really high energy, whereas radio wave photons would have very low energy. The idea of a quantum or a packet of energy, this is very important for spectroscopy. Now, on the other hand, we also have to think about electromagnetic radiation as waves. So we need to think about the frequency, the wavelength, and speed, as well as the relationships between those. So frequency is given the symbol nu, the Greek letter nu, and this is defined as the number of waves that pass a point per unit time. The number of waves that pass a point per unit time. So if, for example, it's 1 wave per second, then this could be defined as 1/second, or s, which is another abbreviation for second, to the -1, and s to the -1 is also known as hertz. Wavelength is symbolized by lambda, and this is the distance between peak to peak or valley to valley. Can't write and talk at the same time. Peak to peak or valley to valley. Now the speed depends on both the frequency and the wavelength, but for all electromagnetic radiation, they all have the same speed, which is c, and this is wavelength times frequency, and for all electromagnetic radiation, this is 3.00 times 10 to the 8th meters per second. It may seem unusual to think about low energy waves and really high energy waves traveling at the same speed, but the speed is common to all forms of electromagnetic radiation. They differ in the wavelength and in the frequency, and therefore they differ in the energy. Now let's consider some relationships. So we just said that c, the speed of light, is equal to wavelength times frequency. We can divide both sides by wavelength, and this tells us that the frequency is equal to c over lambda. So what we can see then is that frequency is inversely proportional to the wavelength. Another important relationship is between energy and frequency, and so energy is equal to h nu, where h is Planck's constant, which is 6.63 times 10 to the negative 34 joules times seconds. You've probably used this in general chemistry, in a physics class. We might do some calculations, but just kind of as a warm-up exercise. So use the book as a reference if you need the value. So based on this statement, we can see that energy is directly proportional to frequency. I'm going to write this up here. Because energy is h nu and nu is c over lambda, we can rewrite this as E equals hc over lambda. So from here, our third important relationship is that energy is inversely proportional to wavelength. So frequency is inversely proportional to wavelength. As the frequency increases, the wavelength decreases. As the wavelength gets longer, the frequency gets smaller. Energy is directly proportional to frequency. So high frequency means high energy, low frequency means low energy. Energy is inversely proportional to wavelength. So long wavelength is low energy, short wavelength is high energy. These relationships are going to be important to keep in mind as we think about spectroscopy. As we think about the connection between electromagnetic radiation and spectroscopy, we have to consider electromagnetic radiation both as waves and as particles. For the waves, we need to think about the wavelength and the frequency. And in terms of particles, we need to think about quantized states. Now let's take a look at the electromagnetic spectrum. We go from gamma rays, X-rays, UV, vis. So even though we are most familiar with the visible region of the spectrum, it's only a very small part of the overall electromagnetic spectrum. We also have infrared, microwave, and radio frequency. So wavelength is increasing to the right and frequency is increasing to the left. Remember that energy is directly proportional to frequency. So over here we have low energy and up here we have high energy. So gamma rays, very high energy, radio waves, very low energy. Because these different types of radiation have different amounts of energy, they will affect molecules differently. Microwaves, for example, can cause molecules to rotate. Infrared radiation can cause bonds in molecules to stretch or bend. Visible and ultraviolet light, this can lead to electrons jumping to excited states. So different types of energy cause different responses in molecules. And many of these different responses have been applied to different types of spectroscopy. With electronic transitions, this is where an electron goes from a ground state up to an excited state, and this is what we observe in UV-vis spectroscopy. Rotational transitions, this is made possible by microwave radiation. So when you are warming up your leftovers in the microwave, you are causing the water molecules to rotate, and then that friction is what heats up your food, always unevenly. But there's also microwave spectroscopy that uses the rotational transitions to give information about molecules. Vibrational transitions, this refers to causing bonds to stretch and bend, and this is the basis for infrared spectroscopy. One more example is nuclear spin transitions. So nuclei can be thought of as little tops that spin, and radio waves can cause the spin to change direction, and this is at the heart of NMR spectroscopy, nuclear magnetic resonance spectroscopy. So spectroscopy is very useful because molecules are going to be very different, and yet similar range of energy is going to cause the same type of transitions in these very different molecules. So we can use a particular type of spectroscopy using a particular type of radiation to give us certain types of information about molecules. Even though our molecules are very different, it's not as if one molecule will absorb infrared radiation to get bonds to bend and another molecule will absorb UV-vis radiation to get their molecules to stretch and bend. There is variation, but still within the same type of radiation. So as we think about energy transitions and spectroscopy, we need to know what energy is absorbed by a molecule. Well, it's a specific amount of energy that affects a change in state. How do we observe this? Well, spectroscopy is based on the observation of the absorption of energy. And so we observe this by looking at a spectrum. And a spectrum shows us the relationship between the absorption of energy and the wavelength or the frequency, for example. So basically, we have to have a source of radiation that shines through, that passes through a sample, and then we need a detector. So we need to see whether the energy from the source reaches the detector or is it absorbed by the sample. It doesn't matter what type of transition we're talking about, but let's say this represents our ground state and this represents some excited state. Well, this is the energy difference between them. Now, we say that changes in state are quantized. So if we apply radiation that is this big, it's not going to be absorbed. If we apply radiation that is this big, it's not going to be absorbed. It's only when we apply radiation that is exactly the size of this gap that the energy will be absorbed. So we might see our spectrum looking at absorbance increasing in this direction. This could be energy increasing in this direction. Forgot to add that. If we start at low energy, maybe nothing is absorbed, nothing is absorbed. And then when this energy matches this gap, then the energy is going to be absorbed. And then it'll go back down to no absorption. So here the energy is too low and it's not absorbed. Here the energy exactly matches the difference between the ground state and the excited state. And then here the energy is too big, so once again it is not absorbed. Now, this ground state and excited state, we talked about ground state and excited state, thinking about electrons, thinking about UV vis spectroscopy, but we can use it a little bit more generally. This could be electrons in the highest occupied molecular orbital jumping up to the lowest unoccupied molecular orbital. That would be energy in the UV vis range. Or our ground state could be a bond at a particular length, and our excited state could be a bond that is stretched. In that case, this energy difference would fall in the infrared range. So whenever the energy of a photon is less than the change in energy between the two states, then no absorption happens. If the energy of the photon is larger than this energy difference between the states, there's no absorption. It's only when the energy of the photon matches the energy of the change in states that the photon is absorbed. Now, another way that we might see our spectrum is to look at percent transmission. So our source of radiation, we're looking at how much of that radiation reaches the detector. If 100% of the transmission reaches the detector, so we're up here, that means the sample did not absorb anything. If the transmission decreases, well, that's because the sample must have absorbed that energy. So here we might see complete transmission, and now we have absorption. And now it's complete transmission. Well, let's say this is the particular absorption of molecule 1, and then we have another molecule, and maybe that absorbs right here. This is molecule 2. So with spectroscopy, we can see this difference, and often that is meaningful. That can be interpreted to give us very useful information. So maybe this is one molecule and this is another molecule, or maybe these are two different parts of the same molecule, but this is what the spectrometer can measure and this is what we're going to focus on a spectrum. So hopefully this gives you a very, very general idea of spectroscopy.